going to present our work on GraphQL APIs for building models, or IFC models specifically. So the motivation already got mentioned in the fishbowl session, I think, and the open BIM session as well. So currently, most information exchange in a BIM context still happens at the level of files. So IFC is extremely beneficial for interoperability, but we're still exchanging monolithic model files, even though if only a subset of the information might actually be required. And with more and more workflows also moving into the web-based or cloud environments, we need a more fine-grained, web-based and API-level access to building model information. The title already suggests we decided to use GraphQL as the underlying API paradigm. I want to give you a very quick introduction. GraphQL was developed as an alternative to REST to solve the shortcomings of REST. It describes a very similar client-server interaction paradigm, but there are some major differences. So contrary to REST, GraphQL exposes only a single endpoint that a client sends a request to. At the core of the GraphQL API, we have a schema strictly typed, which is the contract between the client and the server. And on a high level, GraphQL enables us to request related and heterogeneous resources through a single request and through a single endpoint. So this is the main benefit. Our previous approach was to directly map the existing IFC schema one-to-one into a GraphQL API, which worked for some use cases, but had several limitations that I want to mention quickly because they directly inform the design decisions we took in our current approach. So the first and most obvious one is with a one-to-one mapping, we also inherit the entire complexity of IFC, which leads to very complex schema and very, very complex verbose queries in the end for the client. Second issue are select statements, which are in direct conflict with GraphQL's strict typing model. And this also has to be dealt with in the queries. And then the third problem is that some constructs, specifically geometry, can be represented in very different, diverse ways in IFC. And to query this efficiently, we need to have prior knowledge of how this is structured in our model before we can even write a query, which is not very feasible. So this brings us to our current approach. The goal is to simplify the interface, to make it usable, to most importantly reduce the query complexity. And then also more specifically to enable an efficient geometry exchange, which is not possible with our previous approach. And this builds on 4 key design pillars or design decisions, and I will go over each of them now in more detail in the following slides. So the first point is a simplified spatial structure, and we took a lot of inspiration from the linked building community, linked building data community here. So you can see the spatial structure as laid out in building topology ontology alongside our API, and it's still very close to how spatial structure is defined in IFC, but we get rid of all the objectified relationships that sit in between the spatial entities. This immediately simplifies queries a lot on the client side. The second point are flattened hierarchies wherever appropriate. So in this example, this shows an example of how a property value can be attached to an element in IFC, which includes a lot of intermediary nodes, which offers a lot of flexibility when we talk about modeling, but introduces complexity that is often not necessary for an API. And so we decided wherever this is appropriate to collapse the intermediary nodes and directly attach, in this case, for example, the properties on the elements themselves or the entities. Then the third design pillar or design choice is about geometry, and that's probably the most drastic one. So we decided instead of exposing the entire IFC geometry subtree or subgraph for each element, to take this subgraph and package it into a single node that can be requested in a common geometry format. We call this atomic because now this node becomes the smallest unit that a client can query, whereas with a one-to-one mapping, we can access individual attributes of for example, a single coordinate of a point. I immediately want to mention the limitations of this because we, of course, have lots of information for different or for certain geometric constructs. For example, here we have a simple wall geometry defined as an extruded area or as an extrusion. And if we transform this or convert this into a common geometry format, which is most typically mesh-based, then we lose this original construction logic. However, the advantage is that the geometry is a lot easier to query, and the query no longer relies on the structure of the original structure of the IFC. Then there are two strategies how we can actually deliver this geometry to clients. First one is external, where we just include a reference to an external geometry file in our response. You can see an example of how this looks like on the right side. The second one is to directly embed the geometry into the response, which is typically JSON and GraphQL. With text-based formats, this can be directly included as a string in the JSON itself. For binary formats, we do a text-based encoding first and then include it. Right. And then the fourth and final design decision is a modular schema extension mechanism. So we kept the core schema and the core API as simple as possible, with an easy mechanism to extend the API. So building elements, for example, are represented in a very generic way, and then depending on the use case, these types can be extended or additional types can be added. We implemented all of this as part of a prototype. It's available on GitHub if anyone is interested. It includes the schema definition and also a server implementation. And to validate the approach, we tested this prototype against different information retrieval scenarios and looked especially at the resulting query complexity. This is one example where we have a query in defining GraphQL's own query definition language on the left side, and on the right side is the corresponding result simplified. It's usually a lot longer for a real IFC file. And we can now, inside the query, directly follow spatial relationships, containment relationships, filter, select certain fields. So it gives a lot of power to the clients to decide what information to retrieve. And in a lot easier form than compared to a one-to-one mapping. The limitation, so until now, we only focus on information retrieval, and it would be very beneficial to also look at mutations, so create, modify, and delete operations, which would be well supported within GraphQL. Second is we are using a file-based backend at the moment, so IFC step files and then use IFC OpenShell to access them. Would be very interesting as well to diversify this as well and look at different storage solutions that are maybe also more efficient for information retrieval. Look at other representations here that we can then expose through the same interface. And then I already talked a little bit about the geometry, which is not an easy problem to solve, I think, but it would be worthwhile to maybe look into other formats, maybe something that is closer to how geometry is represented in IFC, or that allows these diverse structures also to be exchanged as in some sort of container. Yeah, with that I'm finished and I'm happy to answer any questions.